Okay, we're going to continue our work in friction by looking at wedges. And wedges basically are an application of friction, taking advantage of friction to be able to do something like move heavy loads. So a wedge, just in terms of description, it's a machine. So you're all comfortable with machines now and that sort of thing. It's basically a simple machine used to move large loads or to do things like split logs and that sort of thing. Why we're concerned with it and why it's in this particular portion of the study is that basically it's to move the wedge, we're overcoming friction. And the key thing is that it's generally significantly smaller. So overcoming the friction is a small thing, but then it allows us then to move some sort of a large load. Very exciting. Typical wedge. Looks like that. What we're doing in it is putting on some sort of a load. And the way it works basically is that we're going to have a normal force on each of those faces. And because there's a normal force then, and there's some sort of contact here, we're going to have then this friction force. Okay, so when we look at this, how many forces are acting at this point? One. Remember, we've broken it up into something that's parallel to the surface and something that's perpendicular to the surface for calculation purposes. But really, it's a single resultant load. And you'll see that the author basically says, now what we see is a three-force system, which is easy to solve, basically. It's got to be concurrent. The key thing is then knowing these angles. Again, we learned that early on the first part of the friction course there. We talked about friction. We can describe it in two different ways in terms of that coefficient of friction, the mu s and mu k. But we can also talk about it in terms of the angle. And the angle was always measured, remember, from the normal to the angle of that resultant. So basically what that does then gives us the ability it makes it easy. Now, we don't have to solve it that way. And as a matter of fact, we'll go through a problem where we solve it two different ways. But since it's just three forces, what we find is that it's usually easy to solve with a force triangle. Just the three forces, and they got to end up at the same point when we're done. And what we'll find is that it's usually going to be case 3 because it's a machine. We're trying to move it. We're trying to either lift a load or split a log or something like that. So there's going to be some sort of impending motion. We're going to do that case 3 where basically we're going to find that maximum friction force and then use that to figure out what sort of force basically I'm going to need to push in this. Like, think about that. I'm going to try to push this into a log. I need to know what those maximum forces are, those friction forces, to overcome. Oh, go right to the problem. If you don't have a handout, you might want to grab one now, but we're just going to start off. That's all there really is in terms of theoretical discussion on it. We're just going to talk about solving the problems then. Oh. Need to hand a bunch out. Everybody else got one? And we've got 2 sides on it, so we'll look at 2 different problems. Get that out of that. Okay, so it always, as engineers, you want to look at the problem and try to figure out, okay, what is it I need to know about this? What's moving? What's not moving? Where are the forces and that sort of thing? So we've got an end of an I-beam, basically, that is supporting about 100 kilonewtons there of force. So we got a force acting down. It's acting on this set of wedges there. There's also this member CD, but we'll note that the member CD is welded to that. So basically, it's part of the I-beam. It's not going to be moving. And what we're trying to do is lift that I-beam up or slide it down, depending on what. And what we've got is 2 wedges here, wedge E and wedge F. Wedge F is sitting on the ground and then attached to E. E is attached to contact with F, and then that member CD there. And what we're going to be asked to do in terms of this is part 1 is determine the P required to raise the beam. So we're going to be pushing it in. We need to think about, again, what motion is it going to be. So E is going to be going in order to lift that up. And then Q will be basically providing the support to keep the I-beam from traveling off into space and stuff like that. So we'll be asked to find that particular piece too. And then the other thing we need to think about is that we're overcoming friction from E there being pushed in there, but we also have that other wedge F, and we need to think about it too because it's not glued to the ground. It's sitting on the ground with a coefficient of 0.6, and all the surfaces have a coefficient of 0.6. So we also have to check when we calculate that force, will that wedge F move out? So we're going to have to check that to make sure that if we put enough force to get that thing to lift, will F go charging off? And if F shoots off, then it kind of shoots our purpose there, and we probably have to apply some sort of force there. So again, when you think about wedges, you need to sit back and look at, okay, what's moving, what's not, what's got friction, what doesn't have it. And oftentimes, like in the EIT exams, they'll give you different surfaces with different friction coefficients, so you have to be careful there too. 'Tis the season. A real singing group today, don't we? Please don't sing. Most people ask me that too. Okay. Okay, so we're going to solve this 2 different ways. I told you we could do it with a force triangle. We can also just solve it with our typical Cartesian. When we get done with it, you'll see why we tend to like to do the triangle if we can, or the force triangle if we can. Hush. Okay, so the first thing is we need to draw the free body diagram and start thinking about which way forces are going. So the one known force we have there is 100 kilonewtons there at the end of the beam. The beam might be supporting something. We got the Q applied there at the end on that member CD that we saw there. And then we got friction. In terms of the friction, there'll be a normal force here. And which way should the friction force be? Opposite Q. Pretty easy. And again, because we're going to be pushing this and trying to get that to move, we're going to take that all the way to the maximum there. We want that to be the maximum value there. And again, that's at case 2.3. Okay, so the first thing we can get out of the way there is that maximum friction force there. And the N1 was very easy to calculate there. Well, actually, before I do that, I should have done this. But again, by observation, we can see that that's going to be that 100 kilonewtons. Okay, so we already solved part B right off the bat there, because to keep that piece in equilibrium, basically Q has got to be equal to that horizontal force of the friction.
Doesn't it not have to equal it, but it has to be less than it? You're talking about max?
If it's not going anywhere, if we want it to be stuck there, yes, it has to be less. But because it is a wedge and it's a machine, what we want to do is push that wedge in there and actually to get it to, so we need to calculate what value I need to get to figure out what that P is to push that thing through. So that's a good point. That we want to take it to the maximum. That's why I say most of the time we're doing it, it's going to be that case 3. We're taking it right up to the impending motion. Now we'll look at the various wedges and see what the force is, and then necessarily whether that F will be moving along. So we'll look at our first one there, E. So we know that that one angle is at 10 degrees. And then again, like we've done with trusses and everything else, we're just going to be applying Newton's law. This is a machine, so we're going to be taking our forces that are known and putting them in an opposite sense. So we solve for N1 over there, and it came out positive, so it was going up on that one. It'll be pushing down on that one. And my FM1 will be acting in that sense, opposite of what I've got on that particular free body diagram. The other thing there we have is the P, horizontal force being applied there. And then we've also got the two forces there from the slight angle there. And the thing that always catches people here is then we're going to have to play a little geometry, figure out the geometry here. And note that that vertical system, that perpendicular system there has just been rotated by 10 degrees in a counterclockwise fashion there, so we're just going to rotate those up. But we need to keep track of that in terms of cosines and sines. See, we got everything there. And again, our motion is this way, so it makes sense that our friction forces will be acting opposite of that. And then all we're going to do is just collect the various pieces there. We've got the minus N1. And this is vertical, I guess. Okay, our N2, again, the angle, the 10 degrees is measured now from the vertical. So I'll be using the cosine times that portion. So I'm getting the vertical portion of that. And the one thing everybody forgets is we also have a vertical portion on the friction force. And the way I've got it shown here is that it will be acting in the opposite end. It'll be acting down. So the vertical portion of that is acting down like so. Small, but still we have to account for it. And that's everything in the vertical direction. Now one thing we'll note, we can substitute in, what was it? 0.3? Yeah. Again, that's the nice thing about breaking it up into that vertical and parallel and perpendicular components is then we can describe that parallel in terms of the friction coefficient there. So basically now we have this equation down in terms of one unknown because we just solved for this one. On that one, we can just carry that over. And just plugging and chugging a lot of sines and cosines and that sort of thing. But what we find is the normal force there along that surface will be a little bit higher. But again, that influences then the friction force, so we have to be careful of that. And we'll see that when we look at the next equation. We have the P. Nicely, FM1 is going to be on that horizontal, so I don't have to adjust that one. Each of these, though, will have components in that direction there. So it has a horizontal component there, but my N2 also has a component in that direction. And then again, identifying things that we already know. We've got this at 30. This is going to be 0.3 of N2. And we've already calculated N2 as 107. And what we find then, to get that wedge to move, to overcome that friction force now, FM1 and FM2, we need a force of 80.3 kilonewtons to get that going. Now, again, as we mentioned before, now we have to do the check. We have to see if wedge F will be moving because it's not glued to anything, basically. It's just depending upon friction sitting there on the ground. So we need to look at that free body diagram. And again, thinking of Newton's third law there, we're going to come back here, and basically this member is in contact with that member, so these forces have to act in an equal and opposite sense. And again, the motion we're interested in is it going to go that way?
Does the weight have no effect on the force? Are we not including like the weight of something?
We're not including the weight of the wedges, but we are including the weight of that 100 kilonewtons of I-beam, basically. And the way it's being transmitted is N1 to N2 portions of this, and then walking back.
So in reality, though, the weight would have an effect on it, wouldn't it? Or just not?
It's creating our normal force, yeah.
Okay.
It's creating our normal forces on those wedges. Think about this one. N1 was 100, right? Because the beam was sitting right on top of it. And because of the angle here, this has to be a little bit higher.
Okay. I feel like there should be another force, like the force of that object's weight.
That would be a possibility if they included the weights. Usually the wedges are so small in terms of weight compared to the load that they're moving, though. We usually ignore them. But you're right. You know, if you want to be precise, we'd probably throw a weight in there, which, depending on the wedge, may then take us out of the force triangle, and we might have to go with the Cartesian system there. And that's why I'm going to show you both anyway. I think you're allergic to math. Okay, let's look at this in terms of, again, these equilibrium equations on this one. Oops, 2. We probably should describe those again. So we've got and again, it's that perpendicular system. We're just simply rotating it by 10 degrees because of the wedge. So we've got the vertical component there of N2. And then the only one, we've got the vertical component of FM12. And again, this is the tricky part. Just make sure you catch both of those forces, otherwise the equations will screw up. So we got the two vertical components of that, and then finally we got N3. Now going back to the point you made there, 100 kilonewtons, does that make sense? Yeah, because the whole system is 100 kilonewtons without the weight of the wedges basically acting on the ground, so we expect to see 100 kilonewtons. So another way of checking yourself, again, I want you to think about checking yourself along the way there. The whole free body diagram should give us 100 kilonewtons for that. And the pieces we know here, so we know all the N2 pieces there. The N3 is the only thing we didn't have there, so we've got those particular pieces in. Now the critical piece, let's look at what the friction force is. And again, we need to pick up all the things that have components in the horizontal direction there. So we've got the horizontal component there of the friction force. I hope I didn't call that M. I don't want that to be M. And the reason why I don't want it to be M, because if it exceeds M, then we're not moving the beam, basically. It's going to go shooting off there. So we do these calculations here. And what we find then is that F3 has to be 50.3 kilonewtons acting in that direction. Now, how do we determine whether it's moving or not?
You do 100 kilonewtons times 0.6, and if it's less than that.
Exactly. So FM3, which I shouldn't have put up there, and the maximum force for this to start moving this way will be equal to 0.3 times N3, right?
0.6.
0.6. Oh, that's right. Yep. And I was telling you about how they'll give you different surfaces like that. See how easy it is to make that mistake? So what we find then is then that contact there, that F3, the force has to be greater than 60 for that to start moving along there. So since that's greater than our 50.3, it sticks. It stays there, basically. So we don't need to basically glue it down or tack weld it or anything like that. Now, that's Cartesian. And again, as we mentioned, if we were throwing weights in there and extra forces and stuff like that, we might have to not use the force triangle. We're going to try the force triangle for the same problem. And again, we'll go back to the free body diagram that we've already drawn. Okay, so a couple of things is when we start using the force triangle, what we're going to go to start describing our friction is in terms of this friction angle. And remember the definition is that the inverse tan of the mu of S, which was 0.3 in our steel-to-steel cases there, was 16.7 degrees, then which describes this angle here. So again, what we've done now is we've taken and we combined our friction force into a single resultant force there. We're now down to a three-force system. So we've got Q, which is a known direction. We have 100 kilonewtons, which is another known direction. And then finally, our R has to get us back to 0.0 for equilibrium. Question?
Isn't phi the distance between FM2 and R, not FM2 and N? The degree, I mean?
No, it's in with respect with our normal force, the bigger force.
Okay.
That's a good way to think of it, though. It's always the bigger force that it's in respect to.
Thank you.
Okay, and then in terms of looking at our force triangle, a couple of nice things there. In this particular one, we have a 90 degree. And then this is also going to be our phi of s, or 16.7 degrees. Now, when we have a force triangle with a perpendicular angle there, we don't need to go visit the law of sines or cosines. I know you love doing that. But basically now, since we have a 90 degree angle, we can use our sine, cosine, and tangent. So note that R1 we can calculate. Oops. So the big leg times the cosine of that angle should give me this 100, or rewriting it. And we can solve for R1, which we're going to carry on down. And while we're here, we can get Q out of the way. So one of the nice things is, especially if we can find something where we have a perpendicular set of forces there, then the force triangle becomes real simple. We don't even have to worry about law of sines and cosines. We don't have to worry about those interior angles. Just get the one angle, you're all done. Okay, we'll look at the force triangle for this guy. And the two known forces that we have is our R1 that we just got done calculating there. Oops, wrong color. Okay, now we need to think about this R2. It's already rotated over counterclockwise by 10 degrees because of the angle of that, right? And then since the coefficient of friction is 0.3 on this one, we also have the 16.7 degrees there. So again, if I were to draw it in terms of a normal force, the normal force would be going that way, and the vertical friction force would be going that way. So what I'm doing is now rotating my R2 over by that same friction angle of 16.7 degrees. Okay, our one easy force to draw in there is going to be the P, which is horizontal. R1 will be like so. And then R2 needs to bring me back home. And then now we don't unfortunately have any perpendicular angles here, so we're going to be resorting to law of sines or cosines, which then means we need to go in and calculate those interior angles there. We'll call that one beta. We'll call this one alpha. We'll call gamma. And then what we're going to do is just apply a little geometry and figure out all the various pieces here. Now we know this angle here is going to be phi of s plus the 10, which is this. Same angle that we just measured there. Okay, so for our alpha, what we'll find is then we know this is horizontal. And then all we're going to do is subtract this combined shift here of the angle of the wedge plus the friction angle there. So it's just simply 10 plus the 16. And we calculate that interior angle now will be 63.3. And then beta is just simply very easy because that angle there is just going to be the angle of friction, since that's based upon a vertical normal force there of 16.7. And two different ways you can do that. You can just simply recognize that it's a triangle, so the interior angles have to sum up to 180. Or to check yourself here, note that we can break this angle into phi of s. And this is phi of s plus 10. So two different ways to look at it, but basically you can get it that way. Okay, so what I'm interested in finding is P there. So I take P and divide it by the angle directly across from it, which is my 43.3. And then the R1 is the one value I already know, right? So that's my known value. I'm going to take that one and then divide it by the sine of the angle directly across from it, which is the alpha, or 63.3. Now, the next thing we need to do is check again that member F, that wedge F, to see whether it's going anywhere. And what we're going to do is check this with angles now instead. So again, we'll go ahead and use our Newton's third law. So we're going to take the R2 that we just got done from free body of E there. And then that angle will be the friction angle plus the wedge angle of 10 degrees. And then thinking about what's going on here. Oops, wrong color. We have an R3 there. We're going to figure out what this angle is. But before we go there, what kind of system is this one now? Two-force system. So equal and opposite. And what? And collinear. That's that cool word we get to use. Impress all of our English major friends. Collinear. So R2 equals R3. The line of action, oops. So basically, that line of action there is going to describe the two forces. They both have to be that in order for that to be an equilibrium. Now, what we can do, though, is check that against the friction coefficient there, the base. So for static friction, if we want it to be held in place, then basically what we're saying is then the reaction, the angle for this needs to be greater for it to be in equal, or for it not to move. So we basically have to calculate the friction angle there, and if it's greater than the angle that we have there that's necessary for equilibrium, then basically it's not going anywhere. If the angle is less, then basically that means it's shooting out. So what we'll find is that's going to be the now coefficient of friction down there, which is now 0.6. And that says for that block to start moving in relation to the concrete base there, it has to achieve an angle of 31 degrees. So what we're saying then is for this thing to start moving, it's going to see a friction then, a friction force now, angled out to 31 degrees. But since for two-force equilibrium, for it to be an equilibrium, it's at 26, it's less than that, which implies then that block will not move, that surface will not move in relation to the surface down here. So two different ways to kind of look at whether you're sliding or not in terms of the coefficient of friction or in terms of the friction angle. And again, the friction angle, as we saw, was kind of nice because it's basically we're just doing a bunch of force triangles. If I don't get through this problem, I'll post it up on the web, but we'll get started on it. Just talk about some of the issues that.
What's the blue line? Is that what
The blue line that I put on there said that that's where that resultant force would be right at impending motion of the wedge against the concrete surface. So in other words, it has to pass that in order for it to go shooting out, which implies then, since my angle of the force there was less than that, it was 26 degrees, then basically it's not moving. It's in equilibrium. Are people comfortable with that? It's a little strange thinking about things in terms of angles like that, but That would be phi m. Yeah, the blue would be phi m. The maximum angle we can achieve. Okay, is everybody else thoroughly confused? You're so honest. Okay, so again, here's a real application. Basically, you've taken a heavy machine piece there or something. You're forcing a 5-degree wedge under it. Coefficient of friction on all of the surfaces is 0.2, so it's a little bit easier. And again, it's going to be that two-step process. What is the force required to get that wedge moving, basically, to get it to start lifting that? And then the other question is then we've got this issue here at B. Again, it's not glued to the ground. There's nothing holding it there, so there's friction there. Now, interesting point, it's a very small area, but remember the friction area, the area is independent. Friction is going to be independent of the area that's contact. So we've got this small area of contact there, but again, we need to find out whether we have enough friction there so when we start pushing that 5-degree wedge under there, that the whole machine doesn't start going off horizontally. So,
It's almost like a pin joint, kind of.
we want it to behave like a pin joint.
Yeah.
And the problem is that because it's not truly fixed there, it could move. So that's why we generally in friction problems have to do a two-step process, or at least on friction problems, in wedge problems. You're going to be pushing something, and then oftentimes you got to check to make sure that the rest of the body doesn't start moving off too. Okay, so we'll draw some, again, your usual first approach to these sort of things is drawing free body diagrams. See what you got. And I suggest when you think about the final and that sort of thing, you'll be breaking things up into pieces. Take a look and see what you got, and then what you can solve. Okay, so we'll start off with our wedge. And again, thinking about what my impending motion is, my motion, I want it to be this way. If I want to lift it, basically I want to scoot the wedge in that way. So I'll draw my friction force now countering that. Okay, so when we draw that, we realize, okay, I've got three forces there, nothing's known. So basically, I don't have anything I can do with it quite yet. So we continue drawing free body diagrams here. This one will draw the machine. So this was our wedge. And again, paying attention to Newton's third law, so I'm going to draw the forces equal and opposite in that sense. That's the forces that it should see. And it makes sense when you think about it. The wedge is going to be pushing, and one of our big concerns is this going to be moving off? So these forces are tending to push that way. Actually put in dimension. And again, we draw this and we find, okay, well, we've got two unknowns, so we'll continue drawing our free body systems. That'd be one heck of a wedge. Okay, so again, this is like we were doing with trusses and that sort of thing. I'm drawing the whole system now. There'll be a P out here. And again, look at the whole system. Note that I'm not drawing those internal forces there because they're now internal. It's in contact. It's internal to this free body diagram. So those forces don't exist as far as this free body diagram is concerned. This is glued together as far as this free body diagram. But with this free body diagram, I can actually start solving for some things there, noting that Bx and Ax are acting along the same line of action. And a lot of these friction problems you'll see are basically solving a two-dimensional equilibrium problem to start off with, to start developing these normal forces and that sort of thing. So we can take this one and note that I can take a moment at B, noting that AX acts through B there, so it won't participate in that moment equation. So I'm just simply doing an equilibrium problem at this point in time. Okay, now the key thing is solving AY and BY. We can go back to our other diagrams here and note that my N1 is actually the AY in that diagram there. So what I've done is I've solved for my first normal force. And the ability of being able to solve for that, again, since my friction force is drawn perpendicular to that, then I can identify the friction force there. And the nice thing then is knowing my friction coefficient there, what I've just done is solve for my first force there. Now I have a two-force system that I can solve for. Things to get out of the way there will you're right. Thank you. I was losing my x's the other day, and now I'm losing my inverses. Okay, and then we can simply calculate that resultant force and angle by just simply recognizing that R1 is just going to be those two pieces. It's composed of two perpendicular pieces there.